Okay. So let me start gradually. So Happy New Year to everybody. So we have a cake as usual. Today we have Garrett to roll. So this is a French king cake. What kind of class is this? I don't know. But, so you're supposed to cut that. I have to teach, so you guys have to cut. And there is supposed to be some kind of tinklet, the small piece, and somewhere in it. So if you find it, you're going to be the king for the rest of the day, which is for the remaining 4 hours or so. Okay, so while those Caltech students are busy cutting the cakes, let me start. So today I will tell you about homotopy.
Right, I'll take over if you want.
Okay, so this is another way to study and classify topological spaces. So homotopy has to do with how you classify map from one topological space to another topological space. And so suppose we have two topological space X and Y, and suppose there is a continuous map from X to Y. Well, we can say that suppose you have two such maps, then we say that two such maps are homotopic if one can continuously deform one of such map to the other one. And we can use this kind of idea to classify this space Y. Particularly useful is the case when this X is replaced by spheres. So Sn is n-dimensional spheres. So in that case, actually the space of such map, homotopically equivalent classes of such map, is going to be endowed with a group structure. So we can study topological property of this space Y by studying the class of such maps. So I'm going to tell you how we are going to construct such classes and how to study them. Now, homotopy is often confused with homology. Homology is that we studied in the previous quarter. So we have to be careful about that. They are distinct notions. So for example, if you have two-dimensional closed surface with, say, various handles like that, and suppose you consider this kind of cycle. This cycle right here is homologically trivial. That you can show that this cycle is in the same homology class as this cycle. And the reason for that is that there is a two-dimensional surface with this and this as a boundary. So that means that this space and this space are homologically, this cycle and this cycle are homologically equivalent. And in particular, therefore, this cycle is homologically equivalent to this one, which slips away. So that means that this cycle is actually homologically trivial. However, homotopically, it is not the case that these and these are homotopically inequivalent, because you cannot continuously deform this circle to this circle, because in order to move this circle to here, you have to break it somewhere, because here you have two circles over here. So you have to break it somewhere. So you cannot continuously deform this over here. So these are not homotopically equivalent. Okay. So that's one distinction between homology and homotopy. Another distinction is that, well, in particular, when you are dealing with a case with n equal 1, it turns out that So that's called first homotopy classes. The first homotopy can be non-abelian. I said that the homotopy, we're going to endow group structure to homotopies. The first homotopy can be non-abelian, but homology is always abelian. Homology group is always abelian. It's actually a vector space. So there are those distinctions that one should be aware of. Okay? So let me start with a case with n equal 1. That is that to classify homotopically class of a map from a circle to the space, which I'm going to denote from now on, M. So this is going to be first homotopy group that I'm going to talk about, or also called fundamental group. So we'll discuss the fundamental group. Okay? So let me first define the fundamental group. So what I'm going to do is this. So suppose this is manifold M. Pick a point where it just has to be topological space. It doesn't have to be so far differentiable manifold. So this can be a topological manifold. Pick a point x0. Okay? And so what I'm going to do is to define a map from an interval 0, 1 to this space, so call it alpha, in such a way that alpha of 0 and alpha of 1 is equal to x0. Namely, it starts with x0 and ends at x0, and it has to be a continuous map. So you have a loop like that. So I'm going to call that as a loop or a closed path starting and ending at x0. So this is just one loop, and then since beginning and end at the beginning point and end point are identified, so you can think of this also as a map from circle to M. So this is what we are going to do. Now, so I have to tell you how to sort of define homotopical equivalence for this class of, for this kind of maps. And we say that suppose you have two of such maps. So alpha and beta both mapping this interval into M in such a way that beginning and ending point are the same. Then we say that alpha is homotop to beta. Cool. So I'm going to denote that with this symbol and call that as homotop. We say that these are homotop if the following is true. So suppose, so this is alpha, this is the image of alpha, and suppose you have yet another map like that, and images like that, so call that as beta. Okay? Again, beginning and ending at point x0. We say that these are equivalent if we can continuously deform this over here. So what it means is that we have to introduce one more parameter to describe this deformation process. So I'm going to introduce this function h of t of s. So this is going to map the product of interval into M. And this is so that this t is just a parameter of this interval, the parameter coordinate on the circle. The second parameter s is a parameter for the deformation. So therefore, at s equals 0, it coincides with this original map alpha. After the deformation, so this is supposed to be a continuous map, so s is going to continuously changing from s equals 0 to s equals 1, and at the end it is deformed to become beta. And moreover, during the process, it has to be continued to be a loop. So that means that at t equals 0 and 1, this has to be equal to x naught for all the value of s. So you have one more condition, that is that h of t equals 0, s, and h of t equals 1, s has to be x naught. So you can sort of draw this kind of rectangular diagram. This is 0, 1, 1, and then say this is t, and this is s, for example. Then over here you have a map alpha. Over here you have a map beta. And this is mapped, this endpoint are mapped to x naught, and this endpoint is mapped to x naught. So therefore, you start with this map alpha, continuously deform that to beta, keeping endpoint fixed. So this image is continuously deformed over here. If such continuous map exists, we say that alpha and beta are homotopy. Okay? I hope that's clear. So, assuming that's clear, I'm going to ask you the first question. That is that show that alpha being equivalent to beta is indeed an equivalence relation. Okay? So that is to show that alpha is equivalent to itself. And the second property is that if alpha is equivalent to beta, beta is equivalent to alpha. And the third property is that if alpha is equivalent to beta, and if beta is equivalent to gamma, then it implies that alpha is equivalent to gamma. So it's fairly obvious how to do that, but it's kind of a useful exercise to try to actually show that step by step using this definition. The first two is really trivial. The third one requires some reparameterization of the parameter s and t in order to show that this combination is the same. But reparameterization of this parameter t itself is a homotopical deformation that you can sort of continuously, if you have different sort of parameterization of this circle, but as far as the parameterization is monotonically increasing, then you can continuously deform one parameterization to the other. So you have to do something like that in order to actually show this. So this requires some work, whereas these two are sort of more or less trivial from the definition. Okay. So assuming that you solve this problem, we have an equivalence relation. So from our discussion from the last quarter, the fall quarter, we know that if you have an equivalence relation, then you can define equivalence class. So in particular, for example, equivalence class of alpha is defined to be all the closed loops starting and ending at the same point, such that this beta is homotope to alpha. Okay? So if we have equivalence class, we can classify space of all such loops into equivalence classes, and these are called homotopy classes. Okay? So each of these are called homotopy class. Okay, so I'm going to go to the very rightmost transparency. Not transparency, the blackboard, excuse me. So far I have defined the homotopy class. Now what I'm going to do is to introduce a group structure, which is that you can multiply one to the other. And that's why this structure is called a fundamental group. We can introduce group structure. That is, that if you have alpha, beta both being loop, then we can define the homotopy class, but not only that we can define homotopy class, but we can also define their multiplications. It's very clear how we should be defining multiplication. That is that if alpha is a loop starting and ending at point x naught, and if beta is also a loop starting and ending at the same point, then clearly we can define composition of the two. That is that we can start from here, come back to x naught, and then go again from x naught to x naught through beta. That's again another loop. Of course, you have to do some reparameterization in order to fit the parameter into this interval between 0 and 1. Because here you start from the parameter t to be 0, goes to 1, and then again start from 0 to 1, so you have to rescale the parameter. But reparameterizing it as far as it's monotonically increasing is also homotopic operation. So we can do that, and so therefore, and then it doesn't really matter how you parameterize it, because all these parameterizations are homotopically equivalent to each other. So that allows you to define the multiplication property. You can show that identity map, that is, that you stay at x naught throughout the whole process, that's going to be the identity. It's clear because suppose you have an identity which maps this interval 0, 1 to x naught. Then suppose you have such a map, you stay there from 0 to 1, and if you multiply another one, you're going to go around beta afterward. By reparameterizing the process, it's the same as just going around beta. So it works as an identity. Inverse is just going around the loop in the opposite direction. And so you can show that, you can see that this defines, well, actually, so that requires some work to show that the going backward is the same as, so let me actually explain how that works.
さん、
はい。
そのパラメータが単調増加でないといけないっていうのはなぜですか？
So he was asking why the parameterization has to be monotonically increasing. Okay, so let me try to answer that question. Well, so we are asking, so alpha is supposed to be a map from 0, 1 to m. So it's coordinate t, and then it's alpha of t. Okay? So I was saying that, well, so this defines a map, certain map t. Now suppose I can define some other map. Suppose you have a function f which maps 0, 1 to another 0, 1. Okay? But suppose this is monotonically increasing. Okay? So this is t, this is f of t. And suppose I define another one by this. Okay? So then I can argue that these are homotopically the same loop. And well, so the way to do that is, so basically try to straighten this out. So you have this monotonically increasing map. And then you want to compare that with a straight map. You can clearly see, well, it requires some proof, but you can see that you can continuously deform this monotonically increasing map to straight map without a program. So that means that more carefully what it means is that there is a family of maps, fs of t, so that at s equal 1, it is the same original map. At S equals 0, it is just linear map like this. So then I can define alpha of, so H of T of S to be alpha of F of S of T. So this is a continuous family of maps. It satisfies the required property because at T equals 0, this is 0, F equals 0, F equals 0 also. So this is x naught. At T equals 1, this is x naught. And then at S equals 0, this is the original map alpha. At S equals 1, this is this map. And this is continuous map. So therefore, you have a continuous deformation. So if you have monotonically increasing map, then you can see that you can continuously deform from one to the other. Now, actually, come to think about that, probably it wasn't necessary even to assume that the map has to be. So if map was monotonically increasing, then this shows that you can continuously deform from one to the other. Okay, now suppose it was not monotonically increasing. Even if it wasn't monotonically increasing, perhaps one may be able to do that. So that was probably the reason why somebody over there. Who was the one who asked that question? Oh yeah. So probably that's why he asked us. You are raising your hand.
It just seems like f needs to be continuous.
Yeah, probably if f is continuous, it should be. So suppose if it's doing something like that, you can still continuously there is still a continuous family of maps which goes from here to here. So that should be okay. So maybe I didn't say it correctly. That I didn't say it precisely. So even if the map is not, the reparameterization is not monotonically increasing, I think that I said that it should be monotonically increasing because if it is not monotonically increasing, it's not a reparameterization. That, for example, here, so the map is not one-to-one, so it's not proper reparameterization.
It
So
can't go greater than 1 because then alpha of f of t doesn't make sense.
sorry.
It can't go greater than 1.
Greater than 1 because alpha.
Well, assuming you can sort of assume that it is defined periodically, for
then it
example.
will be discontinuous.
Is that so?
You'll have no uniquely defined inverse.
As in, if you only.
Oh, okay. Well, I'm not so sure.
Then it would just wrap around twice and then.
Sure, but
No, but it's coming back. The winding number doesn't
If you
change.
define it periodically,
Yeah.
then when it reaches 1, it has reached 0, right? So it's if you start it from.
Yeah.
0,
So it's coming back from here, but then it's. Oh, okay. So you say it has a winding number.
Oh, yeah.
Okay. But suppose if I didn't do that drastic thing,
right, you can still have it.
so I can still have this kind of. You can still do that.
This thing you can straighten out.
So I guess that the restriction might be that it has to be sort of the winding number has to be 1. Because if you of course change the parameter, so for example, suppose clearly, if you say, for example, if you take f of t to be 2t, then modulo 1, this is still a sort of good reparameterization. But but this one is no because this does change the homotopy class.
Right.
So not all the reparameterization is okay. I think that I'm not. So I should have actually looked into that more carefully before I start teaching this. But I think that there are some restrictions on the parameterization. Infinitesimal parameter deformations are always okay. But okay, so thank you for asking that question. So I was talking about defining multiplication. Oh yeah, so I was to say that I was to explain how you define the multiplication and inverse and identity, etc. So I was saying that identity, which is to map 0 to 1 entirely to x naught, is an identity because so what is this identity? Well, this one is actually sitting there throughout the process, And then suppose I multiply to this identity some other loop. Then if in this order, what you do is that you're sitting here for a while, and then after that, by the time you come here, you go around alpha. You can also do this. So this is the other way around. Namely, you first go around, and then after you go through this, you're going to be sitting here for the rest of the time. These are homotopically the same thing, because by reparameterizing it, you can go from here to here and vice versa. Okay? So reparameterization probably in this case involves something like this. So you're going to go like that. So for example, if you have alpha, and if you do the reparameterization like this, what it does is that you go around alpha first and stay the rest of the time. And then on the other hand, you can also do something like you stay half of the time flat and then go up. So that would correspond to this one and this one. And these are homotopic to the original one, which is just going this way. So these are all homotopic. So therefore, these are the same thing. So this is equal to that is equal to alpha. Okay? So that's how you define the multiplication and identity. And inverse, to define inverse, we can see the following. So suppose you have alpha to be this kind of loop. And then I want to define the inverse of alpha. So suppose this is alpha. I want to define the inverse of alpha to be the loop that is going backward along the same path. So suppose you have alpha going this way and alpha inverse going this way. Then we see that we can continuously deform this to a trivial map. Because what you do is you go around here, come back here, but then you cut this. If you multiply them together, well, what you do is you go around here first and then come back, but then you cut this a little bit because it's a midpoint, so you don't have to stick to this end point. And then you continuously deform this map like that. And then it becomes an identity map. So therefore, if you define alpha inverse as a loop which is going backward along the original loop, then clearly this times this is homotopic to the identity. So this defines the group structure for the first homology classes. So here is another question. So here is another question. So suppose the target space M is itself a circle, which you can think of as R divided by Z. Then, so in that case, well, one can show that they are representative of fundamental group by the map of this kind. So you map 0, 1. So you map theta as a coordinate from between 0 and 1. Well, I was using t, so let's use t. Let's map t to x naught plus nt. So this is in R over Z. Well, so as t goes from 0 to 1, at t equals 0, you start with x naught. At t equals 1, you have x naught plus n. N is an integer. You choose n to be an integer. So in that case, modulo z, you get back to the original position. What this is doing is that you are wrapping S1 to the S1, but sort of winding that n times. So you have a circle, you have this target space circle, and then you are wrapping this n times and coming back to the original position. So that's this map. Okay? So what the question 2 is asking is to show that the product structure is like this. So in this case, the fundamental group of a circle, therefore, is isomorphic to Z. So the question number 2 is to show this. Just to make sure that you understand the definition of the fundamental group. Okay, so now let me ask the question number 3. Well, so before I ask the question number 3, so let me point out the following. So far, my definition of this fundamental group, I didn't say that, but so I'm going to denote the first homotopy group by pi 1 of M with base point x0. So pi 1 of M with base point x0 is a fundamental group with base point x0. But, well, so it's sort of awkward to have this reference to the base point. It turns out that if, suppose you have a manifold M, and suppose this manifold has the following property that if you pick any 2 points, x0 and y0, if you can always connect them by some kind of open interval, namely that you can always have some kind of continuous map from an interval to the manifold in such a way that gamma of 0 is x0 and gamma of 1 is y0. Then, for any x0 and y0, then we say that M is arcwise connected. Okay. This is slightly different from the connectedness of the manifold. For practical purpose, we can think of them as the same, but there are some pathological examples where arcwise connected space is not. But these two are not exactly the same. But anyway, so if you have arcwisely connected topological space, then you can show that pi 1 of M of x0 is isomorphic as a group pi 1 of M of y0. So for example, in the previous example that I raised in question number 2, we computed pi 1 of S1 with x0, but the end result was Z, which was independent of x0. And the reason for that is that S1 is arcwisely connected. So if the topological space is arcwisely connected, then we can just call the fundamental group as pi 1 of M without reference to the base point. Okay, so I was stressing the fact that the fundamental groups can be non-abelian, although the example that I mentioned over here is an abelian example, that it was Z in the case when the target space is S1, the manifold is S1, but it's not always the case that, so for example, if you have a surface, two-dimensional surface, so it's the example that I raised at the very beginning. Suppose you have a surface with handles, and if the number of handles is greater than 1, then the pi 1 of this space is non-abelian. And I'm going to describe that later. When you have the number of handles is equal to 1, which is the surface, is the torus, the surface of donut, in that case, the pi 1 is abelian. But if you have more than 1 handle, then you have non-abelian fundamental group. So So perhaps this is the appropriate place to give you one way to describe discrete non-abelian groups. So this is something that probably you learned in one of your undergraduate mathematical method of physics course about group theory. But let me just briefly review that because this is useful way of describing such finite group. So there are many different equivalent ways to describe finite groups, or not necessarily finite group, excuse me, discrete groups. So for example, Z is a discrete but not finite group. So one way to describe those is introduce a notion of free group and relation. So one way to describe discrete group is to introduce first free group and then impose some relation. And you can show that any discrete group can be, finitely generated discrete group can be described in this way. So let me explain that. So first let me define what a free group is. So free group is a very simple thing. So start with a set of letters. So for definiteness, let's say that we have finite set of letters. So it's a set of letters. And then we consider ordered set of letters. So we introduce what's called word. So each word, so this calls that omega, is ordered set of letters. So it's x1 to the n1, x2 to the n2, etc., xn to the nn, where each of xi is either a, b, c, etc. And these n's are integers. So it's ordered product of these words. Okay? And suppose, so when the words repeat themselves, the same letter repeats itself, we can contract it. So suppose, for example, you have a to the n, a to the m, then you can simplify it by writing it as a of n plus m. So for example, as an example, suppose you have a minus 2 b c cubed c minus 2 a e. Then you see that the c is repeated here, so we can replace this by just c. So this process is called reduction. So if you define this operation, if you introduce this operation, then we can make the space as a set of words into a group. It's a very simple thing. That is that basically you just take two words, omega 1, which is a sequence of words like that, omega 2, which is another sequence of words. And if you want to take product, well, you just take product, but just consider combined sequence of letters, and then do the reduction. That is that if the last letter of the first word is the same as the first letter of the second word, then you have to do the reduction, etc. And so by doing that, this becomes a group where identity is an empty word. For example. So by multiplying these words together and reducing the result, we can define multiplication. And this defines for you the free group, F, generated by X. So whenever you have finite set of words, finite set of letters, we can build words, and then you can define free group. It's a very simple thing. Simple thing because there are no sort of relations that just multiply these words together. Interesting fact. So before going into that, let me give you an example of free words, a free group. And this is an example of taken from the fundamental group. So suppose you take two-dimensional Euclidean space, it's a flat space like this blackboard. Remove 2 points, Z0, Z1, and Z2. So these 2 points are removed. So that means that if you have some base point x0, and if you consider loop like this loop cannot be contracted to a point because you cannot cross this point because this point is removed. So this is not a part of the space anymore. So you cannot continuously deform this loop to an identity. Let's call that loop as alpha. You can have another loop like that going around Z2. Let's call that as beta. Then what you can show is pi 1 of this R2 minus these 2 points. So two-dimensional Euclidean space with these 2 points removed is actually free group generated by alpha and beta. So, for example, you can show that. So in particular, this is non-Arderian. So, for example, you have alpha, beta, alpha inverse, beta inverse. If this group were Arderian, then you can commute alpha and beta, and then this would become identity. But you can see that this is not trivial loop. You cannot continuously deform this into an identity map. You go around here, you go around here, and then you go around here backward, and you go around here backward. You can show that you cannot disentangle this loop without going through these points. So this is not an identity. And then, in fact, there are no relations between these loops. Okay, so I'm going to the left part of the blackboard. Okay, so here is the most basic part, most important part for this description of discrete group as a free group with relations. So suppose you take any finitely generated discrete group. So this is a discrete group. I just noticed that on my lecture note I wrote a finite group, so that's a typo. It should be discrete group. And suppose it's generated by A1, A2, AN. Suppose you have n generated. So that means that any element of this group can be expressed as a sort of product of these generators. So suppose you have such description, then, so I'm going to give you a description of G as free group with relations. So how do we do that? So in order to do that, I introduce another group that's just a free group generated by the same number of generators. Of course, these two are different groups, that the multiplication rule can be different. Here it's a free group, so there are no relations in particular. But it is true that you can define homomorphism from F to G. Homomorphism meaning that it's a map from group to group in such a way that if you have a product of two elements here, it's going to be mapped to product of images of each of these elements. So the way that you should define it is very simple. So any element of F would be of this form, A1, N1 to A of I, N, N. So any element of free group is just words built out of these letters. So then I just defined the image here to be this. Okay? You see that this defines a homomorphism. If this is a product, if it is, it's a product right here. But the problem is that this may not be, so this is clearly onto this entire F get mapped to entire G, surjective, but it may not be injective, that it may not be one-to-one. So in particular, non-trivial element, non-trivial words here may be mapped to an identity here. That is to say that there might be a kernel. So kernel is an element of this free group so that phi of G is identity. Now, so here is what here is the part that I cannot give you the proof because this is sort of basic theorem that requires, the proof of that requires maybe half an hour or so. That's something that you must have learned in this group theory course if you have taken that. That is homomorphism theorem. That is to say that image of phi is the same as this original space F, original set F, groups F, divided by kernel of phi. But here in this case, actually image of this map is G itself. So that means that G as a group is the same as free group divided by kernel of phi. Now, so here I also have to introduce one more notion. That is that this kernel of phi is what we call in group theory as an invariant subgroup or normal subgroup of F. That is that so I should write kernel of phi is invariant subgroup. That is to say that if you have an element of phi which I denote as H, then if you take any element of F and conjugate it, it still belongs to H. Also, it still belongs to the kernel of phi. It is easy to show why that is, because in order to show that this combination belongs to the kernel of phi, what you need to show is that the map, this gets mapped to a trivial, this gets mapped to an identity. But, well, if this is a homomorphism, that means that this gets mapped to phi of G, phi of H, phi of G inverse, but phi of H mapped to identity. And then you have phi of G times phi of G inverse, which is an identity. So that means that this is an identity. So that means that this belongs to a kernel, and that's what we wanted to show. So that means that kernel of phi is an invariant subgroup, and it's a basic fact about group theory that if you have a group and if you have a normal subgroup, the quotient is also a group. And it turns out that in this case, it's actually the group that we wanted to understand from the beginning. So what this shows is that any discrete group can be constructed from free group by imposing the condition that any combination that appears in the kernel has to be identified as an identity element. So that's what we call as a relation. The kernel of phi is what we call as a relation. To be precise, what we mean is that any element of H is an identity, is going to be identified as an identity. So you can think of this as a relation between these generators, because so H is a word. So H is a word, and it's mapped to this kind of combination. And basically, we are saying that this is equal to 1. So that's a relation between generators. So this shows that any discrete group can be expressed as free group with a relation. So this is actually a very convenient way to describe finite group, and certainly the case when we are dealing with a fundamental group. So, for example, So for example, if we want to describe the examples that I was talking about earlier, so surface with more than one handle. So I'm going to first introduce the set of generators. In this case, so suppose you have G handles. Then it turns out that we need two G generators. So we pick a base point, x naught, and then first generator, I call that as alpha, 1. And then another generator goes around this handle like that, calls that as beta 1. And then alpha 2 obviously goes around this one like this, and then beta goes around this like that. So this is alpha, this is beta, alpha 2, beta 2. So for each handle, you have generators. So you have alpha 1, beta 1, alpha 2, beta 2, alpha G, beta G. So you have 2G generators. So what you can show is that pi 1 of this surface of what's called genus number of handle G is generated, is actually a free group with just one relation. That is alpha 1, beta 1, alpha 1 inverse, beta 1 inverse goes all the way to alpha G, beta G, alpha G inverse, beta G inverse is equal to 1. So you just consider these two G generators, consider any possible word, but whenever you encounter this combination, you set that equal to 1. Okay? So that gives you the description of pi 1 of sigma of G. Okay. I should say that this is a case for genus G, the number of handle G, greater than or equal to 2. When G equals 0 or 1, the situation is different. Pi 1 of S2 is trivial. Sometimes it's denoted as 1, sometimes it's denoted as 0. So it's trivial. Because if you have two spheres, and if you have a loop, you can always shrink that loop to a 0. Pi 1 of torus, two-dimensional torus, which is denoted as T2, is Z plus Z. So you have two generators, they commute with each other. Okay, so I'm going to the left side of the blackboard. Okay, so I say that if you have any group, then you can consider it as a free group with relations. Now, pi 1 of M is a group. Now, this kind of description also helps you to understand the relation between pi 1 and H1, which is a homology group. So, in some sense, it is sort of abelianization. The H1 is an abelianization of pi 1. So I would like to explain that in a sort of precise manner. So suppose you have a group G. Then there is a subgroup of G called commutator group. It is a group generated by element of this form, A, B, A inverse, B inverse. And you can check easily that this is an invariant subgroup. It's a simple exercise to show that. So therefore, you can divide G by C to define another group, you can show that this is always abelian. So if you divide G by commutator's subgroup, then it becomes abelian. And in fact, you can prove that C is the smallest normal subgroup or invariant subgroup, so that the quotient is abelian. So in some sense, this is a maximally possible abelian quotient construction out of G. So I'm saying that because this is exactly the relation between pi 1 and h1. Namely, h1 is equal to pi 1 divided by commutators. So basically what it means is that if you have pi 1, where you have set of generators with relations, and if you want to construct h1, all you have to do is to ignore the fact that these generators do not commute with each other. So then you get h1. Okay? So that's the description of fundamental group. So now I was planning to discuss yet another interesting class of group called knot group, the group that is associated to knot in 3 dimensions. But in view of time, I will skip that and then discuss higher homotopy groups. Okay, so far we were considering pi 1 of M, and this has to do with homotopy class of maps S1 to M. So natural generalization of this kind of construction is to consider map from Sn to M. And so that's exactly the higher homotopy group. So we could have just said that we're going to consider map from Sn to M and classify that. Well, that can be at the end of the story. But in order to actually define multiplication property of homotopy classes to turn that into group, it's a little bit awkward, but we're going to do this kind of construction. So in order to define this, initially what we did was to consider map from interval to manifold in such a way that initial point and end point get mapped to the same point. So natural generalization of this kind of operation is to consider an n-dimensional generalization of that, which is basically n-tensor product of these intervals. So for example, if n is 2, then you have a square. Then what you want to do, excuse me, is the following. That alpha is called n loop, which is basically a map from Sn to M, but I define it so that it's actually a map from In to M in such a way that the boundary of N gets mapped to some base point x0. So you have this I2 which gets mapped to M, but the boundary are all mapped to the same point. So it's like you shrink this piece of paper and then it doesn't look like sphere, but you should think of this as a sphere because all these perimeters are mapped to the same point. So you can think of, so this is indeed a map from n-dimensional sphere to M. You have a question?
So if your manifold is non-compact, you might not necessarily be able to do that with a boundary, right?
Why is that? Well, the image, we are just dealing with the image. Why the non-compactness is relevant here?
I mean, if you have something that's, if you have a manifold that's diverging, you're not going to be able to contract the boundary all the way.
No, I'm only considering, so I'm not starting from arbitrary map and then contracting it. I'm only considering this class of map from the beginning.
Okay.
I'm not continuously deforming arbitrary map to satisfy this condition. I'm saying from the beginning that I'm only considering this class of map. Or conversely, we can say that if you have a map from Sn to M in such a way that one of the base points, say north pole of Sn, get mapped to x0, you can always have such map described in this way. Okay? But this, so you could have done that, but the reason I'm doing this in this way is this will help us define the multiplication property. So, I also introduced the notion of homotopy equivalence in a more explicit manner. So, okay, so how do you do that? Well, excuse me. So suppose, for example, you have two maps, alpha and beta. Then we say that alpha and betas are homotopically equivalent. Again, if there is yet another map for H of T, S, so T. So for each fixed S, this is a map for fixed S. H is a map from IN to M, so that the boundary get mapped to x0, and then H of T at S equals 0 is alpha. I'm writing this as a vector because this is an n-dimensional space, and H of T with S equal 1 is beta. So this gives you the equivalence relation. So we can consider, so therefore this gives you homotopy class, and the collection of that is going to define pi n of M. Now we have to also define multiplication of two of such things. So if we have alpha and beta as homotopy classes, then we have to define multiplication. So how do we define multiplication? Well, that's where this kind of description in terms of this rectangular space helps, because alpha is a map from this rectangular space into M, and beta is also a map from this rectangular space to M. Then if you want to define a combination of the two, what you do is basically combine these two rectangles together. All the perimeters are mapped to the base point x0. So that means that if you have this combined map where this part gets mapped by alpha and this gets part mapped by beta, where the perimeter here is all mapped to x0 and here it's mapped to x0. So this at the interface, it's continuous, right? So that's a good thing. So that means that we can consider continuous map from this rectangle to M by combining alpha and beta, and then by rescaling this direction, you can shrink that to map from IN to M. Shrinking that is a homotopic operation, so we can do that. So this defines for you the combined map and therefore multiplication of the two homotopy elements. Pictorially, it is just like considering two n-dimensional sphere like that with base point x0, and then another n-dimensional sphere with base point, and they are sort of joined together by sharing this point. Unlike, yes, はい、どうぞ。
それ四角の付け方がいろいろ4通りぐらいあると思うんですけど、それ
はい
って違ったりするんですか？
So he was asking that there seems to be an arbitrariness in defining this multiplication. Because here I'm defining this multiplication along this face, but I could also have defined multiplication using this face or that face. Does it matter? Well, actually it doesn't matter. I think the situation is even better because, in fact, pi n, so this is related to the fact that pi n with n greater than or equal to 2 is actually Abelian. So it doesn't really matter because you can even actually exchange these two. So what happens? So let's see if I have time to explain that. So I'm going to come into this part of the blackboard. So what I did was to consider two map. This is going to map that to m, and then this is going to map that to beta. But then suppose you multiply 2 like that. What we can do is to homotopically change this in such a way that the real action happens in the middle, like that. So what I mean by this is the following. So initially you have this map from alpha to m. So this is a map. Okay. So what I'm going to do is I shrink this region, scale and shrink this region a little bit, and then attach some constant piece outside. So this region is entirely mapped to x0. All these regions are mapped to x0. You see what I mean? So initially only perimeters are mapped to x0, but I can shrink the part that the action is taking place, and the rest, these frames are mapped to x0. That's a homotopic operation. But once we do that, we can do a lot of things. For example, we can shrink this further like that, and then we can move this over here and move this over here. Those are all homotopic operations. So somebody there asked, does it matter how you combine these together? It doesn't matter because suppose, for example, I had multiplied them in this way. You can actually continuously go from here to here because once you have that, once you have this, you can shrink that, and then you can continuously deform that in this way, and then expand, bring that over here. So that means that this product can be turned into this product. So this shows two things. One is that it didn't matter which side that we used to define the product of homotopy group elements. And the other was that the homotopy group is actually commutative. So the higher homotopy groups are commutative. Okay? よろしいでしょうか? Did I answer your question? Okay, so no answer. Okay. So these homotopy groups are very useful thing to classify topological nature of the manifold or topological space. But in fact, it gives you a little bit more refined kind of information. The refined kind of information called homotopy type. So let me explain that. So there are various notions of homotopy. So far we have been using the notion of homotopy maps. That is, suppose you have two maps. If you can continuously deform one map to the other map, we call that two maps are homotopic. So that's what we have been doing. That's the sense of homotopy that we are using so far. That is that suppose you have map F which goes from X to Y, and suppose you have another map G which goes from X to Y. Then we say that F is homotopic to G if there is some map from parameterized by S which maps x to y in such a way that f of s equals 0 is f and h of s equals 1 is g. So if one can continuously deform one map to the other, we say that as homotopic. And it is in that sense that we have been defining homotopy groups. So in that case, I'm taking x to be sphere and y to be the topological space that we are interested in. But we can, so I'm going to the middle blackboard, but we can also define homotopy type of space itself. So, the homotopy types of space is a little bit coarser classification of spaces compared to the topological classification that, as I'm going to explain now. So, suppose we have x and y, and suppose these are topological spaces. Okay? So, we say that x and y are homotopic if there is a map from x to y called f, and then there is another map from y to x called a g, in such a way that f, the combined map, is homotopic to identity on x, because it starts from x and coming back to x. And then G product with F is also homotopic to identity on Y. I'm saying that this is coarser, this is rougher compared to the topological equivalence of homeomorphism, because in that case we require this to be identity. That we require that there is one-to-one continuous map from x to y. In that case, we say that these are topological equivalent. But this is weaker because we are only requiring that to be homotopically equivalent identity. This is, for example, this is weak. For example, if you use this definition, you can show that the space of real numbers R is homotopic to just one point. You can show, you can define a map which maps R to identity. So that's your F, and G is just map P back to R. So suppose P is just one number in R, that is. And you can show that these two properties are satisfied. Okay? So this is an example of what is called contractible space. The space that can be contracted, in this case, to a point. To define contractibility in general, it's useful to introduce a notion of deformation retract. Okay, so that's a following kind of idea. So suppose that so we say that topological space M can be retracted to another space R. This has nothing to do with real number, it's some topological space R. We can say that M can be retracted to R if the following is true. So for example, in this case, space of real number is going to be retracted to a point. This is sort of more general notion. And this general notion goes like that. So suppose you have a map H, which maps, okay, so I assume that R is actually subspace of M. So suppose you have a map from interval times M to itself in such a way that H at S equals 0 is an identity on M. And then at S equals 1, M gets mapped to R, and moreover acts as an identity on R. So what it means is that you have a continuous series of map, which maps at S equals 0, M to itself, but then you can continuously deform this map so that at the end of the process, M gets mapped to R. If you have such a map, such a series of maps, that is, then we say that R is deformation retract of M. And this is an example of deformation retract. You can actually construct a continuous family of map from R to itself in such a way that initially you have an identity map, but in the end, all the points in R get mapped to an identity. You can construct such a map, such a sort of family of map. So in particular, when you have a topological space, and if it is deformation, you have a deformation, you can retract that space to a particular point, then such a space is called contractible. So R is an example of contractible space. Okay. So to take another example, suppose you have a two-dimensional disk. This two-dimensional disk is contractible to a point. But suppose you remove some point in the neighborhood of origin, then this is now you can have an example of deformation retract as a circle, because you can basically shrink this width to a point, to zero width, and then go over here. The reason I'm talking about homotopy classes of spaces, one of which is that homotopy groups are exactly the ones so that you can detect this kind of homotopy types. That one can show that if you have two topological spaces with the same homotopy classes, if you have two topological spaces with the same homotopy type, then they have the same homotopy groups. So for example, if you have a contractible space, okay, so that's a question. Maybe I can pose that as a question. So, and then I guess trying to help solve that could help you understand this definition of deformation retract. If M is contractible to a point, then pi 1 of M is trivial. Okay, so for example, if you have two-dimensional disk, you can contract that to a point, and indeed, any loop in 2 dimensions can be contracted. Okay. So I have 10 minutes or so. So let me give you a few famous examples of homotopy groups. So there are actually quite a bit of difference between homotopy groups and homology. So this actually is going to highlight that. So the first class of examples that I want to talk about is pi n, of Sk. Namely, the homology and homotopy groups of spheres. Oh, excuse me. So in my note, I was using this notation, pi I of n. Okay, so basically what it is dealing with is a map from sphere to sphere. So this is sort of one can think of this as most basic thing. So it's a question of how to sort of consider homotopy type of map from sphere to sphere. That's sort of, you may think that is quite a basic question. But it turns out that it's rather non-trivial. It's rather difficult to program to figure out. So in fact, but actually for pi 1, so suppose, well, let's say that n is greater than 1. So n equal 1 case we already talked about is 1. So then you can show that pi 1 of Sn, pi 2 of Sn, all the way to pi of n minus 1 of Sn are all trivial. This is a sort of generalization of the notion that if you have two spheres, and if you consider loop can always shrink off. So this is a particular example of this, that is to say that pi 1 of S2 is trivial. So in general, if you have a map from sphere to sphere, and if the dimension here is smaller than the dimension here, then the homotopy class of this map is trivial. Okay? So these homotopies are not so interesting. Pi n of Sn is always z. So for example, pi 1 of S1 is z, and we already saw that this is sort of winding number. That is when you map circle to circle, you can wrap circle n times. So that's a winding number. And this is a generalization of that winding number. So these are sort of trivial classes. And then it becomes suddenly interesting when you consider homotopy of pi I of Sn with I greater than n. It's kind of totally opposite of homology, because in the case of homology groups, Hi of n-dimensional space are all trivial when I is greater than n. Here it's totally opposite. That map from higher dimensional sphere to lower dimensional sphere, the homotopy class of such maps are totally non-trivial. So in fact, I think in lecture 6, when we talk about fiber bundle, etc., we discussed the Hopf vibration. Remember Hopf vibration? That was a fiber bundle over S2 with fiber being S1. So you have two spheres with S1 fibered over it in such a way that total space is S3. So that was a Hopf vibration. In fact, the initial motivation of Hopf to come up with this kind of vibration was to understand the map from S3, homotopy class of map from S3 to S2. Because if you have a fiber bundle, what you have is one of the things that you have to have is a projection map from total space to the base. And this is exactly such a map, total space of S3 to the base S2. So this turned out to be this is a non-trivial map, and this turned out to be a non-trivial element of pi 3 of S2. So this is a non-trivial element of pi 3 of S2. In fact, pi 3 of S2 is Z. And so if you remember, we had a classification of a monopole fiber bundle, and then so this is related to the monopole number. So, in fact, the pi I of the homotopy of sphere is not completely understood, and there are lots of unknown territories. But some regularity is known, and one of which is called stable region. That is the following kind of. So it is known that, for example, pi 4 of S3 is equal to pi 5 of S4 is equal to pi 6 of S5. And these are all the same as Z2. Namely, this group generated by two elements squared to 1. Pi 6 of S4 is the same as pi 7 of S5 is equal to pi 8 of S6, and they are all the same as Z2. You see that this number and these numbers are increasing in the same way. So, in general, it is known that if you have pi of 2k plus n, s of k plus 1 plus n, with n is equal to 0, 1, 2, 3, etc., then this depends only on k, if k is greater than or equal to 2. So all these have the same, for some reason that all these have the same properties. And so for example, these are sort of examples. And then this has been computed to some degree, up to some degrees. But totality of that is not known. We have a similar property for homotopy groups of groups themselves. So let's see. So I have only a couple of minutes, so I do not have time to discuss homotopy group of groups. But fortunately, in the next lecture, I was planning to discuss the topology on geometry of groups, group manifolds. So I will defer my discussion of homotopy group of groups to the next week. So I just wanted to mention one more sort of thing before I end. Well, so any lecture on homotopy we cannot finish that without referring to this recent proof by Perelman on Poincare conjecture. So at the beginning, about more than 100 years ago, the Poincare initially conjectured that any three-dimensional manifold with the same Betti number, that is the dimension of homology group, as that of the three-sphere must be homeomorphic to the three-sphere itself. It turned out to be false, that there are some non-trivial example of three-dimensional manifold which has the same homology property as that of the three-sphere, but distinct. So Poincare himself discovered this counterexample and revised his conjecture, saying that if you have simply connected, that is that pi 1 trivial closed three manifold, it must be homeomorphic to three-sphere. So that was a sort of three-dimensional Poincare conjecture. So this has been an outstanding question, and this was actually chosen, and then this was people tried to attack it in various different directions. And it turns out that one could actually prove that in higher dimensional case more easily. So in actually 50 years ago or so, Stephen Smale first proved this conjecture, higher dimensional version of this conjecture for dimension greater than 4. And then I think 30 years ago or so, Michael Friedman proved the 4-dimensional version of the conjecture. And actually, it's kind of important to note that there is a distinction between topological equivalence and differentiable equivalence. Namely, that continuity and smoothness as different things. In fact, there are counterexamples. If you want diffeomorphic version of Poincare conjecture, there are counterexamples that, for example, Milner has shown that in 7 dimensions there are manifold, that the smooth version of Poincare conjectures are false because there are some exotic 7-dimensional sphere which has distinct differential structure compared to the 7-dimensional sphere. But anyway, so about 2002 and 2003, Perelman proved the original version of Poincare conjecture, refining the technique of rich flow by Richard Hamilton. And so finally, this original conjecture by Poincare was proven. So I thought I should mention that because we have been discussing about homotopy group. So next week, I will be discussing geometry of groups, and those are of particular importance when we study one, try to understand various phase transition and phases of matter in condensed matter physics and quantum field theory, and also trying to understand property of gauge theory in Yang-Mills theory. So I view that as sort of quite important subject. So that will be the topic of this lecture next week. Okay, so see you next week.